Hello friends, let us attempt to understand both the mechanical condition and the response of a given category of materials in this lecture. So lastly, in this discussion we will be focusing on metals and alloys, and the mechanical condition to which we will be exposing this particular category of material is uniaxial tensile loading. So we will be exposing this particular category of materials to this form of mechanical condition, which is rather straightforward, or it can be rather illustrated in a straightforward manner if we assume our sample is of this configuration, of this shape here. The uniaxial mechanical loading or uniaxial tensile loading can be represented by these arrows. So we are imposing a uniaxial tensile loading to this particular sample made up of metals or alloys, and we want to understand the response that is rendered by this sample. And on top of it, we want to see what would be the best way of describing both the mechanical condition and the corresponding response of this particular material in a consistent manner. So cumulatively we want to describe both the mechanical condition and the response, and we want to see what is the best way of doing it. Now of course, the conventional way, or one could begin discussing about how for a given mechanical condition what is the corresponding response, and we can extensively discuss on what is the specific response of the material for an imposed mechanical condition. Or another way of approaching the same discussion would be illustrating both the mechanical condition and the response of the material in a single framework. So a conventional way is using purely the verbiage and the theoretical discussions, or just set of equations to describe what is the behavior of the material, what is the response of the sample to the imposed mechanical condition. So the other way of going about would be graphically representing both the mechanical condition and the response in a single framework. So we will attempt to see how we can represent graphically both the mechanical condition and the response of the material in a single framework. So one way of doing that would be an approach that has largely been followed involves considering the response and the mechanical condition in a single two-dimensional coordinate system, wherein the response is considered along the x-axis, while the mechanical condition that brings about this response is considered along the y-axis. So this is the mechanical condition that brings about the response in the material that is considered along the y-axis, while the response is considered along the x-axis. Now there are several ways to quantify the mechanical condition, and mechanical condition being a force, we saw that the relevant parameter that would help us quantify the mechanical condition is nothing but the load. So a mechanical condition, it largely involves, so one typifying feature, one characterizing feature of the mechanical condition is it involves force, and in this context we use the term load, which is nothing but the force. And this load for our consideration is a uniaxial tensile loading, and for this uniaxial tensile loading we expect an elongation, the change in the longitudinal dimension of the sample, which is nothing but the elongation. And this change in the longitudinal dimension or the elongation is quantified as the length at a specific instance to that of the original length. So L is the length at a specific instance and the original length is the L naught. So when I say length at a specific instance, what essentially I am talking about is length for a given loading condition. So essentially what you are doing is, so here in the y-axis you have your load, and in the x-axis you have your elongation. So in this study what you are doing is you are imposing a uniaxial tensile load, and you are progressively increasing the load, and you are correspondingly studying the elongation associated with it. Or a more precise way of looking into this plot is that you are ensuring, or you are progressively inducing a specific elongation into the material, and you are calculating what is the load that is required to bring about the elongation. So you have I have given you two ways of describing what is happening to this system. I will let you understand, or I will leave it to yourself to understand which is the more consistent way. But for our understanding, we can say that we are imposing a load and we are studying the response of the material, even though it is rather inconsistent. For this discussion, without losing any generality, we can say that we are imposing a specific load and we are studying the corresponding response of the material to that imposed load. And what essentially we are doing is, instead of describing it using verbiage, we are plotting it in this coordinate system. Now, when you consider the category, the specific category that we are interested in, that is metals and alloys, it has been observed that through numerous studies, particularly numerous experimental studies, it has been observed that when you focus on metals and alloys alone largely, then the response of the metals and alloys to uniaxial tensile loading, it follows a specific trend. So what you are doing is, you are considering wide range of metals and alloys and you are imposing similar mechanical condition, that is uniaxial tensile loading. And after doing that, you are, instead of discussing it theoretically, you are attempting to render a graphical representation of this form here, wherein you have mechanical condition of the y-axis and the response on the x-axis. When you do that, you observe for a wide range of metals and alloys. For metals and alloys predominantly, they all follow a specific trend, and this trend is of this form here. So this is the trend which you would observe when you largely focus on, or when you primarily focus on metals and alloys. So you are imposing a mechanical condition, uniaxial tensile loading, and you are focusing exclusively on metals and alloys, and instead of discussing it just by words, you are considering graphical representation. And when you notice, say you consider 1000 metals and alloys, so you consider the metals and the combinations thereof and alloys. So what you ultimately end up with, particularly when you represent this behavior using these coordinate system, you observe that there is a specific trend that is followed by, that is characteristic of metals and alloys, and this is the trend that you observe, this is the pattern that you observe. Now, without getting into the specific of it, you could see that this overall pattern, it comprises of 3 different sections. So this overall trend, it can be rather sectioned into 3 different parts. So here, this is the first part. So just by our intuition alone, just by our observation alone, we are able to section this whole trend into 3 different parts. So this is the first part, and this is the second, whereas this is the third. So we have our first section, this is our second section, and this is our third section. So what distinguishes one section from the other? So in this first section, what we observe is, in order to bring about the desired elongation, in order to progressively increase the response, in order to progressively increase the longitudinal dimension of your sample, the load should also proportionally increase. Let me repeat. What is the first section? How is the first section different from the second and the third? Is that in the first section, in order to bring about a progressive increase in the length, the longitudinal dimension of your sample, in order to progressively increase the elongation, the load should also proportionally increase, and this proportionality should be linear. So there is a proportionality, meaning in order to increase the elongation, you should also increase the load, and this proportionality is linear. So the linear proportionality is what characterizes the first section of the mechanical behavior of the metals and alloys. So essentially, this plot, this 2-dimensional plot, is talking about the mechanical behavior. You are imposing a mechanical condition, you are considering its response in a graphical way. And for metals and alloys, there is a general trend, and this trend means this trend indicates, or this trend can be sectioned into 3 different parts. The first part is wherein, in order to progressively increase the elongation, you should proportionally increase the load, and the relation is linear. So the load and the elongation relation is linear. Now, in the second part, even there is, after the first section, in the second part, what we essentially see is, even in this section, in order to further increase the elongation. So you start from here, and when you want to, so you start from here, and when you want to move to this point, so you start from here, and when you want to move to this point, you need to increase the amount of elongation. And in order to increase the amount of elongation, similar to this first section, we have to increase the amount of load that is required. So you are here till this point, you need to have load. To reach this point 1, you need to impose load P1. To reach this point 2, you need to impose an increased amount of loading, that is P2. So similar to the section 1, in section 2 as well, the elongation is proportional to that of the load that we impose. So in the section 2 as well, there is a direct proportionality between the response and the mechanical condition that you are imposing. So elongation on the L is proportional. It's also directly proportional to that of the load. But one distinguishing feature between 1 and 2 is that the section 2 is it is non-linear. Of course, not in the pure mathematical sense, but the way we perceive it, the first section is linear. There is a linear relationship between the load and the elongation, whereas even though in the second section, to bring about or increase the elongation, you need to progressively increase the load. So there is this relation, that is, for increasing the elongation, you need to increase the load. Even though that relation exists, this relation, unlike in the first section, it is not linear, it is non-linear. Now, when you consider the third section, it is in complete contrast to the first two sections. In the third section, what we observe is, in order to increase beyond this point here, when you want to increase the elongation, when the amount of elongation needs to be progressively increased, then the amount of load that is required is not higher but lower. So when you want to move from point 3 to point 4, the elongation from point 3 to point 4, the amount of load that is required is not higher but rather lower. So this could be point 3 and the load that is required for reaching point 4. So what we have is, in section 3, the elongation can be achieved even by increasing or decreasing the load that we have imposed. So what we essentially see in point 3 is a behavior that is in complete contrast to section 1 and section 2. So what we have done is, we have now graphically represented the mechanical behavior of a specific category of materials. And again, this is not a purely theoretical conception. So we have done several experiments and we have observed that these metals and alloys, their behavior, when we represent it graphically of this form, they follow a general trend, and this general trend can be captured by this curve here. So all these understanding, it's gained from a set of experimental observation. So from the real world, we have arrived at this understanding. Now this general trend, this curve, that rather helps us understand the behavior, at least qualitatively helps us understand the behavior of metals and alloys, can be sectioned into 3. And in the first section, you have a linear relationship between the load and the elongation. And in the second section, there is a proportionality, but it is a non-linear relation between the load and the elongation. Again, not purely in the mathematical sense, because there are mathematical description wherein even the second section can be also treated as linear, but we are just talking in terms of our virtual intuition, how we perceive these sections. In the second section, what we see is, even though to increase the amount of elongation, the load should increase, that increase is not linear as we observed in the first section. In the third section, it is in complete contrast to that of the it is in complete contrast to that of the first and second section, because even after decreasing the load, we are able to achieve the increase in the elongation. Now, one other way of looking at this the different sections is that for increasing the elongation, the stress should be, or rather the load, the mechanical condition that we impose should also monotonically, continuously increased. So when you want to continuously increase the elongation in section 1, the corresponding load should also continuously increase. So monotonically it should also increase. The same goes for the section 2. When you want to continually increase the stress, the load, the corresponding load should also monotonically increase. And finally in section 3, when you want to continually increase the response or the elongation, the load in this case monotonically decreases. So this distinction is purely based on how we perceive this particular curve here. We have not so far gone into the material aspect of this curve. We have just looked into this curve, and based on this description alone, based on the way, the trend of this curve alone, we have sectioned it into 3. Now, if you could recollect, just a key point here, if you could recollect, we are able to use the load or the mechanical condition to describe the behavior of a material if we are able to identify a specific or a characteristic behavior, and that allowed us to describe what we refer to it as the failure load, because failure is a specific form of the response that we can distinguish from all the other forms. So when we are able to do that, then we can use the corresponding mechanical condition to describe that particular form of the behavior. So when you are able to distinguish or a specific behavior, then the mechanical condition that brings about that particular behavior can be used to describe it. Now, the reason we considered failure is because that was the only mechanical condition that we were able to conceive then. Now that we have seen there is a specific trend that metals and alloys adhere to, and there are sections and there are characteristic behavior that is possible for us to identify now, it becomes rather relevant, or it becomes rather possible for us to describe or identify these specific behaviors and then use the mechanical condition to describe them. So let me repeat, when we are able to identify specific behaviors, then it is possible for us to describe that specific behavior based on the mechanical condition that brings it about. Now, earlier that specific behavior that we think of was just the failure alone. Now that we have looked into the general trend in the response of the material, in the mechanical behavior of the metals and alloys, and here there are specific behavior that can be realized. Now these specific behavior can be discussed based on the mechanical condition that brings them about. So let us try to identify what these specific behaviors are, instead of giving them or referring to them or attributing a specific name to them. Let us just see what are these specific behaviors first. So you have your section 1, and you have your section 2, and you have your section 3, and this is where the failure occurs. So this is where the failure occurs, and failure meaning we now have one specific response of the material. So here you have your, in the x-axis we have elongation, and the y-axis we have load. So one specific behavior is rather well known to us, and that is the failure. Now, since we were able to distinguish or section the overall curve into 3, there are specific points that indicate the transition from one section to another. So we have a curve, we have sectioned it into 3, and there are specific points, particularly when we are describing the mechanical behavior of metals, there are specific points that indicate the transition from one section to another. So this here, there is one point here that indicates, so this point A, it indicates the transition from section 1 to section 2, and there is a point here B that indicates the transition from section 2 to section 3. So therefore, in addition to failure, we have now identified 2 additional specific responses in the mechanical behavior of metals. Again, the reason we call this particular representation to discuss the mechanical behavior of material, or to describe the mechanical behavior of material, is because it includes both the mechanical condition and also the response. So it gives us the complete picture of the mechanical behavior of materials. Now in this mechanical behavior, in this representation that talks about the mechanical behavior or describes the mechanical behavior of materials, we have identified, in addition to the failure, two specific responses, and since we have identified these two specific responses, we can describe them using their corresponding mechanical condition that brings about these behavior. Similar to the failure, we can now attribute or we can relate these specific mechanical responses to the mechanical condition that brings them about. So therefore, in addition to failure, we are now able to identify two other specific responses, and from these two other specific responses, we are able to relate it to the mechanical condition that brings them about. Now, this term A, like I said, beyond the term A, there is a non-linear relationship between the load and the elongation, and beyond B, there is a inverse relationship, or perceivably an inverse relationship between the load and the elongation. Now, so far again we have not looked into the material aspect of it. So far we have just considered the intuitive. We have given just an intuitive view of this particular load elongation curve, this particular representation of the mechanical behavior of material. We have not considered the material aspect of it. So in order to get into the material aspect of it, what each of these sections mean with respect to the behavior of materials, in order to get into that, let us consider the first section here, the section 1. In section 1, what we observe is, in order to increase the amount of elongation or increase the response that is rendered by a given sample, the load should proportionally increase, the load should linearly increase. So the load should linearly increase in order to bring about the desired elongation. So when you want to have a progressive elongation, when you want to have a progressive increase in the longitudinal dimension of the sample, the load should also progressively increase. Now, in section 1, supposing you are able to arrive at this specific elongation, you are able to arrive at, say, a change dl1. So you are able to arrive at this specific elongation, and in order to arrive at the specific elongation, you are imposing the load of P1. Now, what happens in this section 1 is, once you remove this load, once you remove the load P1, the material, it retracts its path and go back to the point here. So let me repeat, in the section 1, to bring about a specific form of elongation, a specific amount of elongation, you have imposed a specific load. Now, when you unload it, so you have your sample, and this is the length of the sample, and now you are imposing a load of P1, a uniaxial load of P1, and now the size of the sample is the original size plus the elongation. So this is your original sample. Now you have imposed the load of P1. Now when you unload it, when you remove the load, what happens is, the material, it shrink backs, it retraces its path here, it go back to its original state, that is L0. It takes a path and go back to its original state L0. Now again, this state here is the original state. O is the original state. So ideally in the original state, it is important for us to understand, ideally in the original state, there is no elongation and there is no load. So even though it might appear that it is a straightforward aspect of this plot to understand, this will play a key role when we are attempting to arrive at a mathematical expression for the section 1. So what we have is, we have a sample that is held at the original position, and now you are imposing a load P1, and because in response to this load P1, there is a change in the longitudinal dimension, that is dl1. The new dimension is L0 plus dl1. Now when you release the load P1, the system goes back to its original state, wherein there is no elongation and there is no load that is present in the system, that is present in the metals and alloy that we are considering. Now this type of behavior is similar to that of the elasticity that we are familiar with. So when you have a rubber band, so when you play around with it, So when you stretch it for to certain limit and then you leave it off, it goes back to its original position, and this we refer to as the elastic behavior. So elasticity or elastic is a term that we are familiar with in our day-to-day life. So this term or this behavior is the elastic behavior, and this region is referred to as the elastic region. So the section 1 is referred to as the elastic region because the section 1 describes the elastic behavior of the metals and alloys. What essentially you are doing is you are imposing a uniaxial tensile loading, and you observe that once you remove the uniaxial tensile loading, the material gets back to its original state. So within this section here, in this section here, so we considered this particular elongation. Even if you consider this elongation that is close to the point A, even if you consider this elongation D2, that is, you need to bring this about by imposing the load P2. Even in this, for this elongation, when you remove the load P2, the system will get back to its original state, indicating that still the behavior of the metals and alloys is in the elastic region. Still it behaves like an elastic matter. So it still behaves like an elastic system. So this behavior, when you unload the sample and the sample gets back to its original shape, this behavior is called as elastic behavior, and the first section, it describes or it illustrates the elastic behavior of your metals and alloys. So when you say that, so initially when we consider the mathematical aspects of the curve, we saw that in the section 1 or in the first region of your plot, the load is proportional to that of the elongation, and now we saw that this particular behavior, it corresponds to the elastic behavior of your metals and alloys. So it means this particular description, that is the linear relation between the load and the elongation, between the mechanical condition and its response, is in the elastic region. It characterizes the elastic region, or to put it even more sensibly, so to speak, when the material behaves in an elastic way, when the behavior of material is elastic, in that case the mechanical condition that we impose brings about a response that is in linear relation to it. When a material behaves elastically, during this behavior the response of the material is linearly proportional to that of the mechanical condition that we impose. So that is what characterizes the elastic behavior. So we took a materials perspective. So initially we took a purely a theoretical perspective, an intuitive perspective, and we saw there is a linear relationship between the load and the elongation. And when you relate it to the actual behavior that we observe in the sample, the actual elastic behavior that we observe in the sample, then we understand that this linear proportionality is observed when there is an elastic behavior in the material. When the elastic behavior is exhibited by the material, we have such a linear proportionality between load and the elongation. Now, when we say that there is a linear relation or proportionality between the load and the elongation, what it essentially means is that this section 1 is nothing but a straight line. So when we say there is a linear relation, there is a linear proportionality between load and elongation, what it means is that the section 1, the part of the curve, the part of the entire curve that we have considered, the section of the entire curve that represents the section 1 is nothing but a line. So I hope you are convinced with that aspect. So when there is a linear relation, the section that indicates that linear relation is nothing but a straight line. Now again, going back to our mathematical roots, the equation of the straight line can be expressed in the terms of, so we have equation of the straight line that is represented as y equal to mx plus c. So this is nothing but the equation of a straight line. Now if you consider the term c, the way to quantify this term c is nothing but when you have a plot like this. So way to identify the c, or way to understand or estimate the c would be assuming x equal to 0. And when you assume x equal to 0, the value of y will be equivalent to that of the value of c. Now in the plot here, when you assume the x equal to 0, what you observe is the y is also equal to 0. So let me repeat what we are essentially now trying to do is, we are trying to arrive at a numerical relation for the first section of the curve. The first section of the curve, because of its linear proportionality, can or is a line, and there is a numerical expression for the line, and that is expressed in this manner. The expression of the line mathematically is expressed in this manner, and we saw that this constant c can be estimated by assuming x is 0, and in the plot here, when you assume x equal to 0, this y is 0, so therefore the c is also 0. So what it ultimately means is that the first section of this curve here, that is the load elongation curve, the first section of it can be represented just mathematically by this couple of terms. So by this expression alone, you will be able to express the first section of the curve. So in this case, the x is nothing but the elongation dl, and y is nothing but the load. And now the m here in the generalized formulation, in the expression for the line, it indicates the slope of the line, and this slope of the line in the load elongation curve is what it can be replaced, or it is replaced by a constant k, and the entire expression can be written as load k by dl. So what we have essentially done is, we have identified, or we have observed that the first section is a line, and because it's a line, we can describe this first section using the equation of a line, and we have tried to identify what is the value of c, and we have found it to be 0, and then we replaced the slope. So we replaced the y with the appropriate variable, that is the load, and we replaced the x with the appropriate variable, that is the elongation, and also we replaced the slope with the suitable constant, or a suitable parameter. And this is the resulting expression to describe the straight line, the section 1 of the load elongation curve. Now in this expression includes both load and the elongation, along with a parameter that describes the slope of this particular straight line. Now this expression is referred to as the Hooke's law. This expression here is referred to as the Hooke's law because it was Hooke who first identified this linear section, and the constant here that describes this linearity is called the Hooke's constant. So what we essentially have is, we have a straight line that describes the section 1 of the load elongation curve, and this straight line can be described using the different variables that are involved, and we were able to do that by considering the general equation of the straight line and replacing the slope of the straight line with a specific constant, and that constant is called as the Hooke's constant. And we have seen that this particular trend is generally observed in metals and alloys, and there are also materials that do not belong to this category of metals and alloys that exhibit elastic behavior, wherein in the initial stages the load is linearly proportional to that of the elongation. So let me repeat, in addition to the metals and alloy, Hooke during his investigation observed that there are other materials which exhibit this elastic behavior that is characterized by the linear relation between the load and the elongation, and all these materials are, in addition to the metals and alloys, are categorized as Hookean material. Now, when Hooke described this particular behavior of metals to an imposed uniaxial mechanical loading, he used rather some sort of a key phrase to describe this behavior. So in Latin he used a catchable key phrase to describe this behavior of the material, this elastic behavior of the material, and it is written as out tensio sic vis. Now, of course, I know some of you are rather inclined to learn certain words in Latin or in other languages, and you often find some motivational quotes or some guiding phrases that are in Latin or Greek, I don't know. But this is one of a Latin phrase that describes the elastic behavior, that Hooke used to describe the elastic behavior of the materials. That is ut tensio sic vis, meaning the tension, the extension or the stretching of a given material, it depends on the amount of load that you impose. So the amount of extension, the amount of elongation that you observe in a given material is the response of the amount of load that you impose. So this Latin phrase, even though it has maybe it can be used for I don't know, some motivational aspects as well, but this was introduced, or this was the catchphrase when Hooke described this, or when he identified and described this particular behavior of the material. When he arrived at this particular relation, he either topped it all off with this specific or this Latin phrase. So what we have identified is, we have discussed the behavior of a specific category of materials, the one that we are interested in, that is metals and alloys, and we have seen that this mechanical behavior of metals and alloys can be described by considering a graphical representation that involves load and elongation, load along the y-axis and elongation along the x-axis, and there is a specific trend that is followed by these metals and alloys, and this specific trend can be sectioned and specific responses can be identified, and we have now focused on the first trend. And the first trend, there is a linear relationship. That means the first section of the curve is a straight line, and we were able to, from the expression for the straight line, we were able to arrive at the Hooke's law and the Hooke's constant, and this is also referred to as the stiffness. So the Hooke's constant is also referred to as the stiffness. Now, when we consider the graphical representation and we considered load and elongation, there could be an obvious question in your mind as to why should we have to consider load and elongation, because during our previous discussion we have seen that load and elongation, they are not the most ideal way of representing the mechanical behavior and the response of the materials, because load is dependent on load is rather influenced by the configuration of the material that we consider, the dimension of the sample that we have, and the same goes for the elongation. That being the case, why is it necessary for us to consider or begin our consideration with the load elongation curve? So that might be a question, and that is one legitimate question that would have popped up in your mind. Now, the reason such understanding or such analysis, or particularly the experimental analysis, often consider the load and elongation is primarily because often the material that you are using for a specific application. So when you use or when you devise a component for a specific application, there is a specific dimension, there is a particular dimension that is associated with it. So when you purchase a material, you purchase a block of say a steel, and then you process the steel and change it into a component that needs to be used in an application. So consider an aircraft material, and for the aircraft material, or consider a shaft in an automobile, and for this shaft you purchase the material and you transform the material, you process the material, and to bring about this shaft. Now when you want to understand the strength of this shaft, there are two ways of going about it. One is you already know the property of the material, you can estimate the property of the material, and from the property of the material you will be able to extrapolate the mechanical behavior of the shaft. So let me repeat, you are purchasing a material, changing it into a shaft, and now you are attempting to use it in an application. So before using it in an application, you want to know what is the strength of the shaft. So how the mechanical behavior of the shaft would be. So there are two ways of understanding this mechanical behavior of the shaft. One is by determining the property of the material from the property of the material, you can extrapolate, you can discuss this could be the possible mechanical behavior of the shaft. On the other hand, you can devise a mission in such a way that the mission can directly test the entire shaft. So instead of extrapolating the mechanical behavior, instead of talking about the mechanical behavior from this mechanical property, what you can otherwise do is, because the shaft plays a critical role in your application, this particular component which you are interested in is a very critical component. It plays a very vital role in your application. There are lives that are literally dependent on it. So in that case, you don't want to take any chances. So what essentially you would do is, you would build a mission that is capable of testing the entire shaft as it is. So in that case, what you would be imposing, or what you will not be talking about is not in terms of the parameters that get rid of the specifications of, or that get rid of the sample sizes, or get rid of the specification or specific dimension of your shaft, but that includes, you need a parameter that considers these dimensions of the shaft. So therefore, particularly when you are doing an experimental studies, particularly when you are focusing on an experimental studies that are of huge relevance and of huge importance, in that case you would be going for load elongation study instead of the stress strain studies, or you will be going for load elongation representation instead of the stress strain representation. Now, in order to understand the property of the material, in order to have an objective understanding of the behavior of the material, stress versus strain elongations curve could be important. So the stress versus strain curve, these play a critical role when you want to understand the properties of the material, or when you want to have an objective discussion. So objective discussion on the behavior of the material. Objective meaning without any influence of sample dimensions. When these are your condition that needs to be satisfied, then stress strain curve would be your best graphical representation. But when you want to include the influence of the dimension, when you want to study the behavior of a component that is employed in an application, so that is employed in a technological application, then we would often go for load versus elongation plots. For purely theoretical studies, for the laboratory studies, stress and strain curve would be the best way of understanding the mechanical behavior of materials, whereas for the practical application, load and elongation curve would be the best way of describing the mechanical behavior of materials. Now, irrespective of which approach you adapt, the trend still remains the same. The key understanding here is, the key takeaway of this discussion is the discussion of considering the comparing stress, load elongation on the stress strain curve, is that irrespective of which parameter you consider, be it load elongation or stress strain, the overall trend of the curve, it remains the same, because the material essentially that we are considering is the metals and alloys. So again, we are talking in terms of the qualitative trend. So it is possible for us to perceive such a trend even irrespective of what consideration we make. Even in load elongation, we will be able to observe such a trend. Even in stress strain curve, you will be able to observe such a trend. So with this, I would like to wind this lecture up, and in the subsequent lecture, in the next lecture, we will try to identify we will try to rather recreate or discuss the behavior in terms of the stress and strain curves, and in addition to it, we will see what is the equivalence of, or how in the stress strain curve the first section can be described. So in the subsequent lecture, we will largely be focusing on the stress strain representation of the mechanical behavior of materials. Goodbye.